I'm Dave Evans, a PhD candidate from the University of British Columbia. In this video, I'll be talking about JPEG-ACT, accelerating deep learning via transform-based lossy compression. I'm going to get started with some context on the problem we're investigating. The benefits of increased training performance. If we examine image classification networks, it's useful to look at the relationship between the accuracy of a network and how much computation is required to train it. We can see from recent classification networks that accuracy has improved as training performance has increased. Notably, PNASNet uses an architecture search, which increases the total research and training computation by about 10,000 times. Now, if we focus on ACCELERATOR, which restarted interest in convolutional neural networks, the author, Krzyzewski, has stated that he thought he could use GPUs to ratchet up the processing speed of deep neural networks and create a better algorithm. Usually compute drives these performance improvements, but this can be held back by many things. The pursuit of accuracy has a problem. Larger networks lead to more activations and a higher memory consumption. We use the insight that activations look like images. We can use similar techniques to handle both of them. If we examine prior works on activation compression, we can see that lossy precision reduction results in better performance, but some loss in accuracy. Compressing the activations using JPEG leads to relatively poor results. This is because JPEG uses compression parameters that were tuned for images and human perception. By optimizing these parameters, we improve compression and therefore performance, significantly improving accuracy in our work. Our optimization strategy can be extended to most compression methods. JPEG-ACT is an offload accelerator that takes advantage of this compression through a compressed offload and has no changes to the CNN training procedure, no changes to the network architecture, and uses an optimized compression to minimize accuracy loss. In this video, we'll go through some background information on training, an introduction to the JPEG algorithm and why we chose it, the system architecture of JPEG-ACT, the hardware we introduced for the JPEG-ACT accelerator, the optimization of the compression parameters, results, related work, and conclusions. Training CNNs with typical techniques requires the storage of a large number of activations. Let's look at how CNN activation size during training has compared to the available memory on graphics processors, or GPUs. Older networks had a very small activation footprint and easily fit onto a single GPU. Newer models were larger and focused on reducing compute, not memory requirements, so needed multiple GPUs to train. And the newest models require many GPUs to train. This gap is due to physical limitations such as bandwidth and memory technology, and is unlikely to improve as accelerators increase compute densities. As for how this problem actually arises, let's look at training with infinite memory on a GPU. There are two phases of CNN training that cause this, the forward and the backward pass. The forward pass produces activations, and then those activations need to be reloaded in the backward pass. The forward and backward pass also use memory for temporary storage, but mainly it is used as a long-term storage, so I'll ignore this for now. One solution to this is by using VDNN, which effectively expands the GPU memory by paging to the CPU memory. It does this by offloading activations using memcopy to the CPU memory in the forward pass and transferring them back during the backward pass. There are also other techniques which modify these memcopies or use compression to increase the offload rate or increase the effective memory size, but generally the offload rate is quite limited as the PCIe bandwidth is low while activations are very large. Using stochastic gradient descent and the Backprop algorithm results in a training loop with 3 phases. The edges here represent data transfer between each phase. This is a simple CNN with 5 layers. In the forward pass, the input image is passed through the successive layers, which produces the activations, such as R, C, and N. In the backward pass, the gradient with respect to the loss of each activation and weight is calculated, starting from the last layer and going to the first layer. The weight gradients are then used to update the weights of the network, and the process is repeated. Now, as for activations, they need to be saved, as the gradient computation in the backward pass often requires the activations as an input. The deeper the network, the more storage required for activations. Previous approaches have looked at older networks, and we'll shortly see that this isn't applicable to many of the recent networks. ACCELERATOR and VGG mainly used a basic block consisting of a 3x3 convolution, ReLU activation, and dropout. If you look at ResNets, the basic block adds 1x1 convolutions as bottlenecks, skip layers, and batch normalization. Finally, if you look at networks generated by architecture search, for example AmoebNet, the structure is quite complicated. What's important here is that each edge is an activation that might have to be saved. First, I'd like to draw attention to ReLU, which is used widely and creates activation sparsity. This will be important for compression when I talk about it later. Next, dropout is used much less in recent years, but creates highly sparse activations when it is. Finally, batch normalization is a recent advancement that results in dense activations. If we look at all these factors together, we can see that older networks had fewer activations and a high activation sparsity of around 70%, whereas newer networks have a much lower sparsity of around 25%. This is a drastic impact on activation compression, as a lot of prior works use sparse compression. Now we're going to discuss the JPEG algorithm and why we chose it. Our take on the activation problem is to use lossy compression, which is high compression at the expense of fidelity. You can see we have an image here of a cat, and if we discard spatial information, that's discarding some frequencies, we can get a 5x, 25x, and even 67x compression ratio if we use JPEG, and you can still recognize that this is an image of a cat. Now let's talk about the frequency domain and how images and CNN activations are represented in it. JPEG works primarily through the discrete cosine transform, or DCT, which converts an image into magnitudes of these 64 2D frequency components. If we examine the variation of these components across an image, measured here using entropy, we can see that low frequencies, that's to the left, have a much larger variation. The slope profile tells us that there is more information in the low frequencies, or that there is a spatial correlation in the image. We see a similar trend with dense CNN activations, implying that there's also spatial correlation, but the distributions are slightly different. We've found that spatial correlation exists in all layers of all CNNs that we've examined, even deep networks. To compress an activation using JPEG, it's first broken down into 8x8 blocks. We've already talked about the frequency transform, which is done using the DCT. Quantization takes the frequency components and selectively quantizes them according to a set of compression parameters, that's in gray. In JPEG, these are tuned for human perception, but in our work, we demonstrate that optimizing them for CNN perception significantly improves accuracy. In baseline JPEG, these are implemented as a division operation by the values in the discrete quantization table, or DQT. Finally, coding involves removing the zeros and encoding the quantized values for higher compression. In baseline JPEG, this is done with run length and Huffman coding. There are a few other details in JPEG which I'll leave out for now. The takeaway here is that JPEG operates in the frequency domain, and the lossy error is defined by the DQT. The higher the value in the DQT, the larger the quantization of the corresponding frequency. We will now examine the system setup for JPEG-ACT. Out of the options for training CNNs, ASICs, GPUs, and CPUs, we select GPUs as they have a good trade-off of performance and programmability. However, the memory wall is also applicable to ASICs. Our baseline GPU has streaming multiprocessors, or SMs, connected to a crossbar, and a series of memory controllers consisting of L2 cache and a connection to the GPU high bandwidth memory, or HBM. As well, we connect the GPU to an external CPU using PCIe. This becomes our baseline. In order to improve the offload rate, we add compression to the memory system in the form of a CDU, a compression-decompression unit, which is capable of compressing values from the L2 cache before offloading them using DMA. There are some issues with adding compression at the cache, especially if compression spans multiple memory partitions. This requires sharing data between cache partitions, as well as a large hardware overhead from duplication across the many partitions. Instead, DMA side compression makes a single point of compression for the entire GPU at the DMA unit. As JPEG compression can span multiple cache lines, we choose DMA side compression for JPEG-ACT. Please refer to our paper for more details on CDU placement. We use multiple CDUs to allow for multiple mem copies to be processed at once. This avoids issues with saturating the bandwidth of a single cache partition or crossbar link. The collector and splitter units join and split the streams from the multiple CDUs for the single memory stream. Once again, see our paper for more details. In a system with no CDUs, activation mem copies are performed simultaneously with compute. The CDMA work improves this by compressing mem copies to allow for a higher effective offload rate. JPEG-ACT improves this further by providing compression methods that are capable of handling state-of-the-art CNNs. This significantly improves the offload rate. As we add hardware for compression, we add no extra compute overhead and provide a significantly higher effective offload rate than VDNN or CDMA. We will now go over the JPEG-ACT CDU implementation. The first CDU we implement is JPEG base, or a baseline implementation of JPEG. In compression mode, during the forward pass, data moves from the crossbar through the CDUs to the collector and DMA. In decompression mode, during the backward pass, data moves from the DMA through the splitter, through the CDUs, and to the GPU crossbar and memory. I'll move these to the side while we go through the components of the CDU, starting with scaled fixed point precision reduction, or SFPR. CNN activations are stored in floating point, either 16 or 32 bits, whereas JPEG compression operates on 8-bit integers, mainly for area and power efficiency. We've observed that naively casting between these two can cause issues due to the wide range of activation magnitudes, so we designed SFPR to safely bridge this gap. The SFPR unit is composed of 8 parallel processing elements and involves a multiplication by a per-channel scaling factor, S sub c, followed by a naive cast. We reuse the floating point multiplier in both modes by multiplying by the inverse scaling factor when decompressing. The scaling factor is designed such that each channel has a maximum magnitude of S by dividing by the channel-wise maximum and multiplying by a global scaling factor, S. S is selected such that the activation error is minimized. We use a single value of S to minimize the number of hyperparameters in our method, but S can be selected on a per network or per layer basis at the expense of tuning additional hyperparameters. Changing S affects the amount of clipping and truncation involved when casting, which we find has a large impact on JPEG compression. As well, normalizing the scale of activations provides a more consistent compression across networks. JPEG uses a 2D transform, so it requires a filled 8x8 block of activations. In order to achieve this, we use an alignment buffer to align cache lines coming from memory before processing. We employ a few techniques to ensure compatibility between JPEG-ACT and the GPU memory system. We align and pad activations in memory up to multiples of 8, which has less than a 4% storage overhead. We load all cache lines spanned by a single JPEG block and size the alignment buffer to minimize memory accesses by allowing the storage of any other blocks loaded in those same cache lines. The alignment buffer size therefore depends on cache line size, JPEG block size, and the SFPR compression ratio. With 128-byte cache lines, 8x8 blocks, and a 4x compression ratio, this results in a 256-byte buffer capable of holding 4 JPEG blocks. I've highlighted here the JPEG portion of the accelerator, including hardware implementations of the DCT, DIV, and RLE stages of the pipeline. We use implementations from Loeffler et al. And OpenCores, so instead I'll discuss the changes we make for CNNs. So far, I've been talking about JPEG base, a naive implementation of the JPEG pipeline, but now I'll split our design into JPEG base and an optimized JPEG-ACT CDU. Optimizing the JPEG pipeline for CNNs requires changing the quantization, coding stage, and DQT values. The JPEG-ACT backend is different to allow for higher CNN compression and reduced hardware area and power. I'll get to the DQT changes in a minute, and we'll talk about the quantization and coding changes first. The baseline JPEG pipeline uses division of the DCT output by the quantization table. This is a relatively expensive operation in terms of hardware, involving 64 multipliers. To reduce this, we replace the division by a shift and present shift quantization. For example, the 6 is shifted by a 1 and becomes a 3. In terms of coding, in our paper we find that run-length encoding does a poor job of extracting zeros from quantized CNN activations in the frequency domain. This is due to the different frequency distribution of CNN activations when compared to images. We use zero-value compression, or ZVC, to better extract zeros after quantization, which involves extracting a bit mask, which indicates the position of the non-zero values, and removing the zeros. Combining these two results in 3/4 the area of the JPEG base CDU and increases compression by 30%. Finally, we also include units for non-JPEG compression in the CDU. Mainly this is due to sparse activations, which still make up some portion of modern CNNs. We include JNet-All's binary ReLU compression, or BRC, and add a bypass for SFPR and ZVC. I'll quickly break down how we select a compression method given an activation type. Sparse activations followed by a convolution layer use SFPR, or SFPR followed by ZVC, if it's available. Otherwise, sparse activations can use JNet-All's binary ReLU compression. Dense activations with a width of 8 or more use SFPR followed by JPEG, and otherwise use SFPR. This results in 1 to 2/3 of CNN activations being compressed with JPEG, depending on the network. I'll now go over our process for tuning JPEG-ACT for CNN compression. We would like to maximize compression while maintaining network accuracy. Starting with some trained network, if we take the compression parameters and simulate compression, then estimate the final network accuracy and JPEG compression ratio, then we could use this to update and optimize the parameters for CNN compression. Note that we are not using this to train the network, we are optimizing to improve the compression. The network training process is not affected in any way. The JPEG parameters are the quantization table, and as for updating, we chose to use SGD for this process. Once again, we are not using SGD on the network, we are using it on the JPEG parameters. We use a network with frozen weights as the input to the algorithm. We use Shannon entropy, H, to estimate compression, which gives the bits required per activation. Estimating the accuracy is much more difficult, as training is stochastic and non-convex. In the paper, we describe an approximation where minimizing the L2 activation error will lead to similar accuracies as training without compression. We combine these two terms into an objective function, with lambdas being scaling factors to adjust the magnitudes. Alpha controls the trade-off between accuracy and compression, similar to the quality setting in JPEG. This objective isn't specific to JPEG and can be used to optimize any parameterized compression method. Here are three methods when examined on the error compression landscape. Better results are to the lower left, signifying better error for a given compression. Each line corresponds to a compression method with different parameterizations. The SFPR line is for different bit widths, for example, 3 bits. The image DQT line is for JPEG with different quality settings, for example, 60 and 80. Finally, the green line is for optimized DQTs with different values of alpha. When alpha decreases, we can see that optimization favors higher compression. When optimization increases, we can see that lower compression is favored. All points along the optimized line improve the Pareto frontier for compression and error, meaning that optimization is always better than SFPR or naive JPEG. From this, we pick two optimized DQTs, high compression opt-H and low compression opt-L. Using opt-H results in a 1.5x compression improvement over JPEG-ACT. Estimates of error and entropy are not static over the course of training. Here we've plotted these terms for ResNet-50. On both plots, lower is better. On the left, error relates to the accuracy of a network after training. On the right, entropy relates to the compression of the activations. We go into more detail on how these metrics behave during training in our paper. The most important conclusions that we come to are that despite changing parameters past epoch 5, entropy, and thus compression, remain mostly constant during training, and that piecewise training can be used to clear high error periods early in training. We label this as opt-L5H. Briefly, this means to anneal at low compression for 5 epochs before switching to high compression. On average, JPEG-ACT provides a significant increase in performance over VDNN, 2.6x, with significantly improved error versus unoptimized JPEG. If we examine individual network performance, we can see that performance gains are primarily made on networks which include bottlenecks, for example, ResNet-50. Methods focusing on highly sparse networks, such as CDMA and GIST, show poor performance on these deep networks. On average, JPEG-ACT achieves 1.6x performance versus GIST. Now we'll examine compression. On the left, we have various combinations of JPEG backends, and along the top, different quantization tables. If we examine the effect of optimizing JPEG for activations, we can see that optimizing the quantization table significantly increases compression. And when combined with the backend improvements, the compression ratio improves from 5.3x to 7.9x for a 50% improvement. If we look at where these improvements are occurring on VGG, we can see that JPEG significantly improves compression of convolution activations, and by adding zero-value compression and a more aggressive quantization table, compression of dropout and convolution activations increases again. On ResNet-50, as there are no dropout activations, JPEG-ACT has a larger relative compression ratio to the other methods, as 3/4 of the network is dense activations. We see similar trends for the ImageNet and Div2K datasets. Let's finish up. When compared to prior works that handle activations during training, JPEG-ACT is the first to incorporate lossy compression into an offload accelerator. Many previous approaches, such as reversible residual networks and WAGE, require extensive network constraints or modifications, which is not required with JPEG-ACT. Memory-centric deep learning is an interesting approach, but usually requires expensive interconnects, such as NVLink, to operate. Even so, JPEG-ACT can be combined with this approach. We compare favorably against VDNN, CDMA, and GIST in our work, showing that JPEG-ACT has a lower performance overhead and higher compression ratio. In conclusion, in this video, we've presented JPEG-ACT, an offload accelerator for deep learning. For more information, see our paper in ISCA 2020, and if you have any questions, visit our question and answer period at 1:15 p.m. Eastern Daylight Time on Wednesday, June 3rd. Thanks for watching.